So let's check out surface integrals now. Essentially, it's kind of like line integrals where you had a curve in space and you found that a function f of x, y, z was defined on the curve. And so you added up all your function values along this curve. And we called that a line integral over c of f of x, y, z ds. And that little ds, that little piece was one little piece of the curve there. Now, surface integral is kind of the same idea. You have your same old function f of x, y, z. This d capital S now, though, is a little piece of your surface. So you have a little piece of the surface, and you're going to take a representative function value there, f of xi, yi, zi, for example. You're going to multiply that times your piece of your surface, add all those up, and that'll be your surface area. Now, that little piece of your surface, that's curved, so what we're going to do is we're going to approximate that with a tangent plane, like we did in section 16.6. So, like right here, we approximated the surface with a little tangent plane area. So that was before, that was this business right here, where it was the cross product of these two vectors that formed the tangent plane. So that gave you your n, and then you found the absolute value, the magnitude of your n to find the area of the surface. So what we're doing here then is we're going to multiply by that little, this is the area of the surface multiplied times your function value. Now, the function value, you're plugging in r of uv into your function, because that's kind of what you did before, right? In order to solve this, remember, this was f of r of t, and then multiplied times r prime of t dt. The length of r prime of t dt. All right, so this here was that d little s piece, and now this here is the ds piece, this right here, all this. Okay, so you're basically plugging your parameterization of your surface into your function to perform this double integral, okay? And actually that's what they're saying right here. You know, compare these two, they're pretty much very similar. All right, so let's try this one. Compute the surface integral x squared ds, where s is the unit sphere, x squared plus y squared plus z squared equals 1. So we have the unit sphere. Let me draw this in black. And you have a unit sphere, and we're performing the double integral of x squared ds over the sphere, over capital S. So you're taking a little piece of your surface, and you're finding x squared there, whatever x value is there. You're taking that and you're adding that to other pieces of your surface. Find out what x squared is, other pieces of your surface. Find out what x squared is. Adding all these up. Okay, so we need to parameterize this sphere. I think the sphere was a unit sphere. Yeah, unit sphere. So it was x squared plus y squared plus z squared equals 1, which can be parameterized using r of phi theta, which is rho cosine phi sine of theta. No, what was it? X equals rho cosine theta sine phi. So this one would, rho is 1 in this case, so it's cosine theta sine phi. Y was sine theta sine phi. And then z was, rho is 1, so it's cosine of phi with this. All right, so that's r. Now, whenever we perform the integral, we just use the x squared, so we're going to square this and put that in the integral in just a minute. Now, we need to find that RU cross RV. So to do that, it doesn't have to be U and V. Here we have theta and phi. So R sub phi is cosine theta cosine phi, and then sine theta cosine phi, and then negative sine of phi. That, and then R theta is negative sine theta sine of phi, cosine theta sine of phi, and then 0 for the last one, because it's just cosine phi, and we're doing R sub theta. So now you perform the cross product. So what I'll do is I'll perform this cross product. I'm going to pause the video and do it, and then you check it out and see if you understand it. All right, so this is what you get when you cross them. Now let's find the magnitude of that. So I'm going to take the square root of the first one squared will be cosine squared theta sine to the fourth of phi plus sine squared theta sine to the fourth of phi plus cosine squared phi sine squared phi. So I can pull out a sine to the fourth phi here, and I'll get cosine squared plus sine squared. So that'll be sine to the fourth phi, and then sine to the fourth phi plus cosine squared phi sine squared phi. Now I can pull out a sine squared phi, and when I pull it out, it comes out sine phi, and I get sine squared phi plus cosine squared phi, which is 1. So out of all this, I just get sine of phi, which is, if you look, if we had the rho on here, if rho was on here in the r theta, if this was rho and then rho and then rho here, we would have had at the end rho sine phi, which is just the Jacobian. So if you look back at 15.9, you'll see that really this is just the Jacobian that we found before for spherical coordinates. All right, so but in this case we just have sine of phi, so we're going to use this right over here. So I'll pull this over, and now it's double integral x squared will be, okay, so let me pull out all these little rows. Cosine phi, cosine theta sine of phi, so that would be cosine theta sine of phi, quantity squared, that's the x squared, and then sine of phi, and then d phi d theta. You don't need the Jacobian here because we never started out with x, y, and z. We're not doing a conversion here. We're not doing a transformation. Okay, so this is over d here. Okay, now d is no longer the shadow in the xy plane here. It's going to be what we started out with phi and theta, the domain of phi and theta. So if phi is here and theta is here, for the sphere, phi goes from, let's see, it goes from 0 to pi. And then theta goes from 0 to 2 pi, right? So we have theta going from 0 to 2 pi, and then phi goes from 0 to pi. And now this is just a trig problem from here on out. You probably have to, you can actually split this up into integral cosine squared of theta d theta times the integral, this is 0 to 2 pi, and then times the integral of sine squared phi sine theta, sine phi d phi from 0 to pi. So then you probably have to use the cosine of theta equals cosine squared of theta is 1/2 times 1 minus or 1 plus cosine of 2 theta. And then here, you'll split that sine squared of phi into 1 minus cosine squared of phi, and then use u substitution with u equals sine phi, and continue on. The answer is 4 pi over 3. All right, so that's one problem. Now, an application of this is whenever you have, like you could have this be a lamina, so a thin sheet, and F is the density everywhere. And so here you can find the total mass, or maybe it's the charge density, and so then you're going to find the charge, the total charge current. So then we have some applications here. You can find the center of mass as well using these. So I'll let you work those out. Okay, so here's if the surface, it says here, if the surface is given by a function of z, let's say z is g of xy, g of xy. All right, so then remember from the previous section, then r of xy will be x comma y comma g of xy. So when you find the we need to find the length here, this length, it's no longer in terms of u and v, all right? It's now in terms of x and y, and the parameterization is different now. So what you can do, see, it's no longer, when you parameterize it like this, okay, when you parameterize your surface like this, r of uv, all of these here, the x, y, and z, are functions of u and v. They're all functions of u and v, all right? But whenever you have z equals a function of x and y, all right, then these two pieces are just single parameters. They're just the parameters themselves. So we went over that in the last video. And so your n value, your n, will be g sub x cross g sub y, and you'll get this here. I think I did that in the previous video. It'll be negative g sub x, comma negative g sub y, comma 1. And then when you find this, the length of that, so n, the length of n, remember the length of n will be the area of a little tangent plane piece that approximates your curve. So if this is your curve, your little tangent plane piece, it's going to be approximated using an n vector, right? Which gives the length of that, gives you the area of that tangent plane. So here's the area of your surface piece here, times your function values, and this will give you your surface integral. Okay, so this example walks through that using that new formula. So it's pretty straightforward. This here says if S is a piecewise smooth surface. So notice that this surface, this is a surface, it's the top, the bottom, and all the sides. So it's this here, it's this here, and it's also that bottom piece here on the bottom. So it's 3 of them. So it's piecewise smooth because, we say piecewise smooth because this edge here, this surface here, S3, and this surface here, S2, I think this is S1, sorry, S1, when they meet, it's not smooth, but it's piecewise smooth. So the pieces are smooth themselves. So what you have to do is you have to do all of these separate. So it's double integral over S1. The integral is z ds, so d z ds1, plus the double integral of z ds2 over S2, plus the double integral of z ds3 over S3, like that. So you split them up and you do all of them separately. And the hard part is finding this piece here, because it's it could be different everywhere. So like for example, here S2, n points straight down. So n will be 0, 0, -1. It's the outward normal. And then on this one here, okay, we can use the cylindrical parameterization. Let's just do it. Let's just do that side one. So you have a piece of the cylinder there. All right. So you have a cylinder like this. So the parameterization of that, let's see, x could be what is it, 1? Is it radius 1? Yeah, the radius is 1. So you could have r of theta comma z, could have that being cosine theta, sine theta, and then just z itself. So for every z value, you get a new circle. So it's just a bunch of circles, one on top of the other. Okay, there you have it. So now we still have to find r sub theta across r sub z. So you do all that, negative sine theta, cosine theta, and then this will be 0, and then r. This would be, okay, so I'm doing r sub theta. So r sub theta is this. R sub z is 0, 0, 1. So then r sub theta across r sub z is, let's see here, it's going to be cosine theta, sine theta, and then 0. So what happens here is this is your n vector, and it looks like there's only an x and y component to it. So the z value is 0. So just as, so notice that it's the same as that, right, as the beginning. So what's happening here is the following. When you, let me see, let's go back to this. When you, a point on each circle is described using a vector coming out from the origin. And that point, let's say z is 0, will be described using cosine theta. Well, let me draw it further up. Cosine theta, sine theta, and then 0. We're assuming we're looking at the circle that's in the xy plane. If we're up top here, then z will be some constant. So this would be a constant, not 0. Okay, so to find the normal vector, okay, so a tangent vector to that circle looks like this, right? So a normal vector will just be the continuation of that. So it'll be the same exact vector. And that's why we got it. That's why we got that. But it's going to be, it's not the same exact one. In the xy plane it is, but as you move up, there's a z value. So there would be, so for this one here, there's a z value, say it's 2. But the normal vector would be continuing out, but it doesn't have a, look, this is what's happening. Yeah, so you have your vector that goes like this, right? And then that would be cosine theta, sine theta, and then z. And then now this is your normal vector coming out where your normal vector, sorry, it's the circle, and then the z is always 2. So it's this circle, that's this. And then your normal vector comes straight out. So then now that's going to be 0. All right, so that's it right there. Okay, so this is an example in the book. So so in fact, it's a video example. They actually do it. So I invite you to look at that. Okay, so while you're in the book, I'd like you to read about what an oriented surface is. Basically, it just says that the surface has an orientation and that the positive orientation is outward. So if you have your like sphere, for example, the orientation is outward. The positive orientation is outward. The negative orientation is inward. Now, there are surfaces that are non-orientable, for example, the Mobius strip. So you can look that up. It's kind of an interesting idea. And then they go back and they talk about the normal vector and then the unit normal from that. All right. But what I really want to get to is surface integrals of vector fields. And so this is where we get into what's called flux. So if you have a surface integral, if you have a surface and you want to find the flux of a, or the outward flow, you want to find the flow per unit area of a vector field through the surface. Let me just draw it over here. So you have a surface, and you want to find, so you have a surface, and then you have a vector field going through the surface. This F. Let's say it's like this over here as well. And it's like, maybe it goes like this over here. Okay. The flux is the amount of the velocity field that's actually going through the surface. So if there's a vector over here that is parallel to the surface, then there's no flux going through it. Okay, so part of the vectors are like this over here. They're not going through the surface, so the flux should be zero. So the flux is the outward flow, or the flow through the surface. All right, so in order to measure that, it would help if we had a normal vector. So I'm going to look at a normal vector to the surface, and I'm going to compare that to the the vector field there. And it depends, it says, I mean, it's kind of obvious that if this angle is called angle theta, if that angle theta is 90 degrees, then we have the scenario like down here, right? We have this, if it's 90 degrees, then they're perpendicular, and the cosine of 90 is 0. So if the, on the other hand, if that normal and the vector field line up, then the angle there is 0. So here the angle is 0, theta equals 0, and the cosine of 0 is 1. So the most you can get out of the most flow through this permeable surface will be whenever the vectors are along the same lines and theta is 0. The least amount is this scenario here. I'm sorry, not this vector, but that vector there. And that's where theta is 90 degrees. So this brings up the dot product, okay? So the flow, so the flux is going to be, is governed by the vector field dotted with n, because f dot n, remember, is the length of the vector times n times the cosine of the angle between them. And the minimum is when theta is 90 degrees. Maximum is when theta is 0 degrees. Okay, so that's why the dot product comes up. All right, so if we want to find out the total flow, we're gonna take a, let me make this so that it doesn't look perpendicular. Maybe it's like this, and then the angle. So then this is your surface. And so the angle here is not 90 degrees. So here's theta, it's not 90 degrees. So what you're going to do is you're going to take a little area of the surface, right? And then find the flux there. So we'll find the flux here, F dot N, and multiply it times that area, and then add all these up. This gives you what's called the flux, and it's right here. So little area of the surface times F dot N, that gives you the flux of F across S. And then these formulas come from that. All right. So now this here comes from, this is a nice little formula here that you're going to be using quite a bit. F is, so when we do F dot ds, let me show you that one. So suppose F is P, Q, and R, so it's some vector field, and then R of UV, I think are these in X and Y? Yeah, they're using X and Y. Yeah, so R of X and Y, so these is X comma Y comma G of XY. So this is where your surface will be given by Z is some function of X and Y. So like Z equals X squared plus Y squared, maybe, the bowl, right? Okay, so now whenever you do F dot N, all right, N comes from this, right? And so remember, we found N to be negative G sub X, negative G sub Y, comma 1. So when you do F dot N, you do PQR dotted with this, you get the double integral over S F dot N ds is going to be the double integral of, now you do the dot product, so it's negative P G sub X minus Q G sub Y plus R over S. And now we're going to use the domain of our X and Y here and integrate over that. And so that's where they get all of this. Okay? And so then they give you some examples of this. So maybe in another video, so electric applications, electric flux is a good one. All right? And then you get to this in thermodynamics. Heat flow is another one. All right? And so they give you some exercises to do. So maybe in another video I'll do an example.